Okay, so we are back. Now there will be a stream of lightning talk sessions. We have 3 of them, unless someone else steps forward. And the first speaker is Philip.
Sure. Hi, I'm Philip. I'm from CamConcept. I'm involved in a nice project called Exploits, and notice the D, not the T. So, what's Exploits? The long title is Explicit Privacy Preserving Loss Intrusion Detection System. So what we want to do, we want to have some loss intrusion detection system on some machine, and we want to do some privacy preserving data collection and analysis. And it's a research project together with the University of Dresden and Leipzig and some other corporate partners. And sorry, the slide is in German, I haven't had the time to translate, but I will do my best. So that's the big overview, and what I'm currently working on is this gray area, which is L4RE, and our virtual machine monitor called the UVMM, and there will also be some intrusion detection system hardware and front-end machine. So you have like the virtual machine on one side, you have the virtual machine monitor below, and then you have Linux running in that virtual machine. And if that Linux is attacked, then you want to apply some exploit by any attack vector. You want to detect that, and then you want to switch on some sensors to see, okay, now we get attacked, and now we want to log as many information as possible about this attack to be able to essentially replay that attack, and to detect the vector of intrusion. And so, therefore, to detect all that, we have project plan is to have some sensors in the virtual machine. So it's not the concept that you are not detectable by the attacker. The concept is that you can even then detect the attacker and log what he's doing. So you have sensors in different levels in the operating system, for example, some Linux kernel module. You have some system services, and you have at the application level you have some logging capabilities, like, for example, the ZIH of the TU Dresden. They have a tool called Vampire, which profiles an application, and if something goes there, then you can detect that somebody is fiddling with that application. And then we get to the privacy preserving part. You have some host running that virtual machine, and you have there the sensor injection. So you say, all right, I want to collect this data and that data, and the virtual machine monitor and the kernel module your Linux guest system supports the injection of that sensor, so you can communicate and you can get more data, and then you extract the data, and you want to keep the data as anonymous as possible to detect. So that's to be able to replay that attack. So that's ongoing research by the TU Dresden's data security group. And then you want to anonymize the data and get it off the host, because you don't want your even in the case that your host is compromised, then you still want to keep the data and be able to replay the attack. The replaying thing is important, so you have a back end of the network where you do forensic analysis, where you do graph analysis of the data you collected, and you may decide which sensors to switch on and off. And then there's the whole other part of that project, which targets that you can reuse the data and visualize them to allow a judge to understand what happened, so that the judge can understand who was the attacker, how he did it, and so that he can come to a good sentence or a good outcome of that process. it's not only the microkernel virtualization part, it's also the part the privacy preserving. Have some database which allows to do data mining on encrypted data, and it's the visualization and explanation to a non-techie person how this all happened. And that's the project what I'm currently working on. With our goals, we port our virtual machine monitor to the MD64 platform. So we have several virtualization solutions, but our virtual machine monitor, which is for ARM, for MIPS, and now for MD64. We want to do some introspection and debugging of virtual machine snapshotting. And there's also some hardware purging involved in the form of an FPGA, which can do memory accesses, and you run areas that can do memory accesses, and extract the data without help of the CPU, or a lot of help from the CPU, the cryptography and the anonymization, and then send it off to the database on the remote server. Yeah, that's exploits the talk. And if you have questions, I will be around later. Thank you.
So our next speaker and the presenter of the next lightning talk is
hello. So this is my pet project. It's very experimental, very unfinished, so keep that in mind. First, for a little bit of motivation, I primarily work on Helenos, like terminal operating systems. It supports many platforms. It also supports, still, I don't know why, Intel 64 architecture. And the problem with that is that LLVM and by extension Rust doesn't support that architecture. The support that did exist is, I think, kind of broken and completely unmaintained, so it's not really an option to use it for anything that needs to be reliable. And that means we have to find some way to get Rust on Helenos that can cope with this problem. One of the options is, of course, to just ignore the architecture. Another option is to ignore Rust. But I opted for a third option. And I tried to solve this by building Rust to WebAssembly, which it supports, and then translate the WebAssembly to C, and compile the C as you normally would any application. WebAssembly is a binary distribution format developed primarily for use on the web. It is basically a virtual instruction set architecture. It has a set of instructions, and it has execution semantics for those. It is designed to be secure, which is important for us because reasons. And it is quite simple, actually. It is easy to work with, and since it's primarily a web technology, it is also has basically lots and lots of users, and there are tools existing to work with this format. It is technically it's a stack-based virtual machine, which to some evokes certain problems, but in this case the stuckness of it is basically it's a representation metaphor. It doesn't really depend on there being a stack of values. It directly translates to static allocation. So you can just go through the code and make static variables from those slots on the stack. So this doesn't really make it any worse than say LLVM, and compared to LLVM, this is portable, this is completely platform neutral, where LLVM, basically when you compile something to a LLVM, you cannot run it on another platform than what it was compiled for. The LLVM bytecode is still specific to some architecture, even if it's not fully compiled yet. Whereas when you compile to WebAssembly, you really can run it everywhere. And it is the exact same semantics, exact same behavior, and one of the important things is also that it basically supports checking memory accesses very simply. It's built in. so you don't have to worry about that. Even if, for example, if your system lacks memory management, or for example, you don't even have MMU, you can still run WebAssembly programs, binaries compiled that you don't trust at all. You can be sure that they don't access anything they shouldn't. Rust, you probably already know. There was a presentation before that explained some of it. It has LLVM backend, supports WebAssembly natively, and it is interoperable with C API, which, when compiled to WebAssembly, translates to imports. WebAssembly has a native concept of imported functions, which is what you can use here. So when you translate WebAssembly to C, you, as I said, stack slots map to local variables there directly. There is no explicit stack manipulation. Most instructions are not understood by the translator at all. I need to understand some basic things like control flow, for example, loops, branches, that kind of stuff. But most instructions, you just need to know how many stack slots they consume and how many are stored, which is currently 0 or 1. So as you can see here, for example, the add instruction for the 64-bit integer gets translated to something like this. It just takes the variables corresponding to the stack slots, calls a function on it. That function, you can define it any way you want. You can make it an inline function in the same module as the generated code, for example, so that the compiler inlines it. And imported functions get translated to external C functions calls, so you can easily call functions. And basically, any API you want to expose, you can expose with C code. For this, you can't actually directly pass pointers between the WebAssembly code and native code, but you can make bindings which take care of that. And this is part of the safety requirements, that you can't just pass any pointer. That pointer is indexed to some local span of memory, some local buffer, and you need to take it into that account. And as I said, the translator itself is very simple. It's just a few hundreds of lines of code, and it's quite crude, but GCC can optimize most of it away, so it doesn't harm performance any. And it is very flexible because, as I said before, most instructions are just calls to sub-predefined names. So you can define, for example, if you want to really check some operations, check memory accesses, you can. If you don't want to check memory accesses, you also can. Just depends on the way you implement those C schemes. That's pretty much it. No more slides. I don't know how much time I spent. Okay, so that's it. If you have any questions, you can ask me later. Thanks for listening.